We talked a lot about lithium-ion battery testing next door, so I want to show you a little bit about capacitor testing. You know, these are potentiostats. They are devices that apply voltages and measure currents. Our users use them for electrochemical sensors, corrosion, all kinds of different types of applications. So I want to make sure we pick on something that was not batteries for this type of work. So again, that's part of my puzzle. The demo I'm going to run and am currently running is a 3 farad capacitor. And so we'll walk through that and show you exactly what it looks like. But there's some different techniques. I also brought 50 farad capacitor that we can run with a PMC 1000 with its 2 amp capability. And I brought the 3000 farad capacitor that we can run with the 10 amp booster connected as well. And so it kind of walks through. We'll do some cooking show type science today, right? We'll start the experiment. Boom, I'm gonna hit a button over, and we'll let it. We'll show you what the end result would look like. But one of the things I'm gonna try and highlight here is while we had the experiments, while we had the presentations running next door, I started this experiment on a capacitor. But you saw me take this computer with me as I went over there to give that presentation. And so that highlights one of the technical differentiators between this product, and that is the fact it's got a buffer on board. And so it's got this 4 to 6 million point buffer decided depending on which model of potentiostat you have. So I came over and started the experiment, pulled the cable, took the computer next door. So really it's a protection mechanism in case there's any USB communication. Everything runs on board on the potentiostat. So as I open up the Versus Studio software, hopefully this will work seamlessly. And over here I have the 2 channels represented by the PMC 1000, 2000. We'll talk more about them when the differences between the two as it comes over, and the different highlights of that kind of chassis. But if I just click on this value, then and open up that experiment. Boom, all the data that we've been acquiring this whole time kind of feeds through. I can show that to you more as you kind of come over here. But now I have, let me pop over and we'll have the data associated with this 50 farad galvanic static EIS test. So I can come here, we can insert different types of experiments. One of them being linear scan voltammetry, right? Because I'm doing a cycle voltammetry. So this is going to be the mechanism by which I charge and discharge the capacitor, right? This is essentially what an analog scan generator would do for your experiment. And so we're going to charge that up to that level, and then we're going to run over and run a galvanic static EIS test. As I said, these potentiostats are multi-purpose. They can do a lot of different things. From voltammetry to corrosion to impedance to energy techniques. Once I have acquired this data, I can then move over to a fitting software program. Allows me to paste the data over. And then I'm going to select a model and run the fit. Now, what did you notice I did not do? What do we normally have to do when we do EIS fitting results? Input a initial parameter, initial gas rate. And so this has an algorithm that kind of helps you with that. It kind of determines the initial value guess and starts doing those iterations from that value. We did not input the value. So normally what you would do is select an initial estimate to give the fitting algorithm some direction. So if you have, and you can lock them down as degrees of freedom. So if you have an R, a Randall cell, an R with an R and C In series, normally we would want to input in an initial estimate of those values. But here we were able to accomplish a fit without those initial estimates of those values. And then we can come back out and we can see that I have fit the first R value to 13 milliohms. This is on that 50 farad capacitor. He was specified as under 20 milliohms ESR. And that's typically how you're going to see those capacitors. The spec is an ESR under a certain value. Then we have a 49 farads. It fit to 49 farads. So that's the value of my 50 farad cap. Let me make sure I keep this one short and sweet. And so we can then run over here and do these as CVs. A CV is of a supercap, should look like a box, right? If I integrate that supercap in this way, I can get down to about a 53 farad charge. Other techniques or things like that cyclic voltammetry. We know when we increase the scan rate of cyclic voltammetry, the total current passed is going to be higher. And so on this 50 farad capacitor, I was able to scan at 25 millivolts without a booster, because I've got a 2 amp capability. Those are those values overlaid. Constant current to charge and discharge that capacitor, and then galvanostatic DIS. This is what the 3000 farad capacitor looks like. You can see even at 2 millivolts per second, it generated 7 amps of current. So that is why I have a booster here. 2 slots, same chassis, user installed booster, selected in. Same kind of charge-discharge through a constant current. So again, we talk about capacitors and batteries are using the same types of techniques, right? I'm using CV, I'm using constant current, I'm using galvanostatic DIS. And then here's the fit to a 3000 farad capacitor, right? I have a very low ESR of 8 milliamps and a very high capacitance value. But anytime you make the measurement, we talked earlier today about the making sure that your instrumentation is capable of making this measurement. How do I go back and make sure I'm really measuring the cell? And we would do that with dummy cells. We would do this with high precision, low value resistors. And so here was a 1 milliohm resistor, and here's a 10 milliohm resistor. And the fact that I can measure the 1 milliohm resistor accurately and a 10 milliohm resistor accurately states that, through the same setup, states that 8 milliohms is truly from my capacitor, right? I'm not picking up, it's not the noise, it's not the floor of the